Hello, and welcome back to the quiet cosmos. Tonight we are looking at two planets that never quite finish. Jupiter first, and then Saturn. And what waits at the bottom of each one is not a place to arrive, but more of the same fall. We begin at the top of Jupiter's clouds and go straight down, through gas that slowly stops behaving like gas, into an ocean of hydrogen pressed until it starts to conduct electricity like a metal, past a small probe that fell for less than an hour before it went silent, and out again to 4 ancient moons, a faint ring of dust, and a comet that came apart on its way in. Before we go any further, if you enjoy this kind of unhurried astronomy, a like or a subscribe helps these long, quiet films find the people who are actually looking for them, and it costs you nothing more than a moment to do. After that, the same descent happens a second time at Saturn, through a paler and quieter atmosphere, hiding the very same bottomless structure underneath, out to rings built from countless separate pieces of ice, and up to a 6-sided pattern of cloud that has been turning at its pole for longer than anyone has been watching it. With all of that ahead of us, the fall begins now, at the only edge either of these two planets actually has, the place where the atmosphere starts and simply never stops. Jupiter is the largest planet in our solar system, wider across than 11 Earths placed side by side, and yet it has no surface for anything to land on. There is no coastline, no plain, no rock underfoot anywhere on this world, because Jupiter is built almost entirely from gas, and gas simply keeps going. What looks from a distance like a solid golden sphere banded in cream and rust is actually only the very top of an atmosphere that continues downward for tens of thousands of kilometers before it becomes anything else at all. Everything that has ever been sent into this atmosphere has kept going until it was destroyed by pressure and heat. Tonight, we follow that fall as far as anyone currently understands it, from the pale clouds of the top, down through an ocean without a shore, into a metal made of the lightest element there is, and toward a center that resists being pinned down even by name. Jupiter is built from almost the same material as the Sun itself, a mixture of about 3/4 hydrogen and 1/4 helium by mass, with only a thin trace of heavier elements folded in. This is not the composition of a rocky planet slightly puffed up. It is closer to the leftover material of the very cloud that formed the solar system, gathered together but never given enough mass to ignite. A star needs roughly 80 times Jupiter's bulk before the pressure at its center grows fierce enough to force hydrogen nuclei together and start the reactions that make a sun shine. Jupiter falls a long way short of that threshold, and so it sits there, warm from its own slow contraction but dark, radiating a dim glow of infrared light rather than visible fire. Astronomers sometimes describe it as a world built from star stuff without a star's ignition, which is one way of saying it is closer in kind to the Sun than to any of the rocky worlds nearby. What it lacks in fusion, it makes up for in depth, because that same hydrogen and helium, given enough pressure, is capable of behaving in ways no laboratory on Earth can easily reproduce. By mass, Jupiter is more than twice as heavy as every other planet in the solar system combined. A single body outweighing Saturn, Uranus, Neptune, Earth, Venus, Mars, and Mercury, all added together with room to spare. Its gravity is strong enough that the Sun and Jupiter technically circle a shared point, sitting just outside the Sun's own visible surface, a detail usually ignored because the Sun is so much heavier overall, but a reminder of how unusual Jupiter's bulk really is among planets. That gravity reaches out far beyond the visible cloud tops, shepherding smaller bodies, bending the paths of comets, and holding together a system of moons that in some ways resembles a miniature solar system of its own. None of that mass, though, has ever compressed into anything a foot could stand on. Every additional layer of pressure below the clouds squeezes the same hydrogen and helium tighter, changing how it behaves without converting it into rock or metal in the ordinary sense, until very much deeper than most people imagine. Weight on this world does not lead anywhere near a flaw. Jupiter orbits roughly 5 times farther from the Sun than Earth does, a distance great enough that sunlight arriving at its cloud tops carries only a fraction of the intensity it has here, and a single circuit of that orbit takes almost 12 of our years to complete. From so far out, the Sun would look like a bright point rather than a wide disk, and the light falling on Jupiter's clouds is closer to a cold, pale afternoon than to full daylight. Despite that distance and that comparative dimness, Jupiter is not cold all the way through, because whatever warmth it lacks from the Sun, it makes up for later from within itself, once the descent through its atmosphere has gone on for a while. At this distance, the planet also has time to gather an enormous family of moons and a faint system of rings, spread across an orbit so wide that Earth would fit comfortably inside a model of Jupiter's own moon system without leaving much space at the edges. The scale of the neighborhood matches the scale of the planet at its center. The face Jupiter presents to a telescope is a shifting pattern of cream, tan, and rust-colored cloud, streaked into long streams that circle the planet at different speeds, depending on how far they sit from the equator. Those colors come from small amounts of sulfur and phosphorus compounds carried up from deeper layers by rising currents of gas, chemicals that darken or brighten depending on how much sunlight and radiation they have been exposed to near the top. What looks like a fixed painting from Earth is, up close, a boiling and constantly rearranging surface of ammonia ice crystals condensing out of the atmosphere the way frost forms on a cold window. Except here, the window has no far side. Storms rise and fall within these clouds on a scale that dwarfs anything Earth's weather produces, some lasting mere days and others persisting for generations. Among them, a vast red storm wide enough to swallow more than one Earth, which has churned south of the equator for at least a century and a half. The deeper story of this planet, though, lies not in any single storm, but underneath all of them. Descend below those clouds, and the first thing that becomes clear is how little there is to mark the transition from one layer to the next. On a rocky world, the atmosphere thins until it meets solid ground, a boundary any visitor could point to. On Jupiter, the atmosphere instead grows steadily thicker, the gas around a falling object becoming denser and denser, without ever hardening into anything a person would call a surface. Pressure builds the way it would in a diving bell, sinking into an ocean with no seabed, climbing past what Earth's atmosphere manages at sea level within the first 100 kilometers, and continuing to climb for tens of thousands more after that. Temperature rises too, slowly at first, and then more steeply, reversing the pattern familiar from Earth's own sky. Where the air cools, the higher one goes. Here, the arrangement is almost turned inside out, with depth. Cold at the top where sunlight is faint, and warmer the further down the fall continues, all the way to values no organic material could withstand for more than an instant. Beneath the visible clouds lies a series of hazes too thin to see from outside, layers where sunlight breaks apart simple molecules and stitches them back together into smog-like particles that drift for years before settling further down. Instruments looking through this region in ultraviolet and infrared light have mapped a rough structure of ammonia clouds near the top, a band of ammonium hydrosulfide clouds beneath that, and a layer where scientists expect water ice and water droplets to form somewhat deeper still, matching the pattern seen in miniature in Earth's own clouds, but stretched across an atmosphere many times larger. None of these boundaries are sharp lines a probe could register as it passed through them. Each one shades gradually into the next, the way twilight shades into night, without a single moment anyone could call the exact edge of daylight. A century of telescopes and a handful of spacecraft have sketched this structure from the outside, inferring what lies beneath the visible cloud deck from the chemistry of light reflected off its top. Because the interior itself has almost never been visited directly. In December 1995, a single small probe actually did what almost nothing else ever has, dropping directly into Jupiter's atmosphere on a parachute after being released months earlier by the Galileo spacecraft passing overhead. It fell in fast, protected at first by a heat shield that burned away most of its own mass on entry. And once the parachute opened, it began radioing back readings on temperature, pressure, wind speed, and the chemistry of the gas rushing past it. For 58 minutes, the numbers kept arriving, describing winds far stronger than expected and far less water vapor than models had predicted. A small mystery still discussed today. Then, at a depth where the pressure had grown to roughly 20 times what Earth's atmosphere exerts at sea level, and the temperature had climbed past what any of its electronics could tolerate, the signal simply stopped. The probe did not reach a floor because there was not one waiting for it, only more atmosphere, thicker and hotter than the atmosphere just above, continuing on beyond the point where the instrument itself could keep functioning. Continue past the point where the Galileo probe lost contact and the atmosphere keeps thickening, until gas stops behaving like gas in any way a chemist on Earth would recognize. At a certain depth, the temperature and pressure both cross a threshold beyond which hydrogen exists as what physicists call a supercritical fluid, a state with no clear boundary between gas and liquid at all. Under the ordinary conditions found on Earth, water either boils away as steam or settles as liquid, one state or the other, with a sharp line between them. Push the temperature and pressure high enough, though, and that line disappears entirely, leaving a single continuous fluid that never has to decide which phase it is in. This is thought to happen inside Jupiter, only a few thousand kilometers beneath the visible clouds, meaning that anyone hoping to mark the spot where gas becomes liquid on this planet is chasing a boundary that, according to the physics involved, does not strictly exist. It continues, denser with every step, into something that is no longer quite one thing or the other. Further down, once the fluid has thickened enough that most descriptions simply call it liquid, Jupiter holds what amounts to an ocean of hydrogen far larger than anything found on a rocky world, extending across many thousands of kilometers of depth rather than a few. Unlike Earth's oceans, this one has no seabed at its lower edge and no surface at its upper one. Only a very slow gradient from something thinner to something thicker, wrapped entirely around the planet in a shell about as deep as Earth is wide. Waves barely make sense in a fluid held under such pressure, though slow currents and convection almost certainly stir it, carrying heat up from below the way water in a pot begins to circulate once it is set upon a flame. This liquid hydrogen layer is also where scientists believe the planet's supply of helium starts to behave differently from the surrounding hydrogen. No longer content to stay evenly mixed the deeper the two of them travel together, which sets up the next stage of the fall. Deeper still. Hydrogen and helium stop mixing evenly and begin to separate, in a process astronomers call helium rain. Under the pressures found some 10,000 kilometers below the cloud tops, helium no longer dissolves completely into the surrounding hydrogen, and tiny droplets of it condense out the way water condenses from humid air. Except here, the droplets are made of a noble gas falling through liquid metal rather than falling through air. Those droplets, heavier than the fluid around them, sink slowly toward the center over the course of the planet's long history, carrying gravitational energy inward as they go and releasing it as heat along the way. This single process helps explain something that puzzled scientists for years: why Jupiter appears to have less helium near its cloud tops than the Sun does, as though some of the planet's original supply had quietly gone missing. It has not gone missing at all. It has rained downward, drop by drop, across billions of years, gathering somewhere deeper than any instrument has directly measured. A slow and completely silent kind of weather, happening far beneath any cloud a telescope could ever see. Keep descending and, at around an eighth of the way to the center, hydrogen undergoes its strangest transformation of all. Under pressure exceeding 1,000,000 times what Earth's atmosphere exerts at sea level, the hydrogen atoms are packed so closely together that their electrons stop belonging to any single atom, and instead move freely through the fluid. The same arrangement found inside ordinary metals like copper or iron. Hydrogen in this state conducts electricity, reflects light in ways closer to liquid mercury than to gas, and behaves in almost every practical sense like a metal, despite being built from the lightest and simplest element that exists. No laboratory on Earth can sustain a large sample of it for more than an instant, because reproducing the pressure required takes machinery capable only of a brief pulse before the apparatus itself gives way. Inside Jupiter, though, this metallic hydrogen forms an ocean of its own, deeper and denser than the liquid hydrogen layer above it, extending across a volume large enough to swallow several Earths several times over. Here, inside this strange metal made from the simplest atom there is, the next part of the story begins. That ocean of metallic hydrogen does not simply sit there. Convection currents move through it as the planet slowly loses heat from its interior. And because the fluid conducts electricity, those moving currents generate a magnetic field the same way a dynamo does, through motion rather than through anything solid or magnetized in the everyday sense. The result is the strongest magnetic field produced by any planet in the solar system, many times stronger than Earth's own, generated entirely by a fluid that never stops moving and never settles into a fixed shape. Unlike Earth's field, which is reasonably steady and well aligned with the planet's spin, Jupiter's field is tilted and somewhat lumpy, shaped by the uneven currents deep in the metallic layer that produces it. Spacecraft passing close to Jupiter have to be built to withstand this field directly, because it does not fade away gently at the cloud tops, but continues outward for an extraordinary distance, carrying charged particles with it, and turning the space around the planet into an environment unlike anything found closer to the Sun. Jupiter's magnetic field inflates a region of space called the magnetosphere so large that, if it could somehow be made visible in the night sky from Earth, it would appear wider than the full moon, despite being hundreds of millions of kilometers farther away. On the side facing away from the Sun, that magnetic bubble is dragged out into a long tail, stretching well past the orbit of Saturn, making it, by some measures, the largest continuous structure in the solar system after the Sun's own outer influence. Trapped inside this magnetosphere are intense belts of radiation, charged particles accelerated to extraordinary speeds, strong enough that a spacecraft lingering too long in the wrong region would have its electronics damaged within hours rather than years. Engineers designing the Juno mission had to route its orbit carefully through gaps in this radiation, rather than circling the planet at a convenient distance, threading a narrow path each time it passed close. Because the alternative was slow destruction by a field that never turns off and never grows any gentler with time. Some of that trapped material eventually spirals down along the magnetic field lines toward Jupiter's poles, colliding with the upper atmosphere and producing glowing rings of light circling each pole, similar in cause to the aurorae seen occasionally on Earth, but far brighter and almost permanently present rather than a rare event tied to solar activity. Much of the material feeding these glowing rings does not come from the Sun at all, but from Jupiter's own volcanic moon, which constantly sheds charged particles that the magnetic field gathers and channels down toward the planet. Telescopes able to see in ultraviolet light have photographed this glow directly, showing structure and flickering detail rather than a smooth, uniform ring. Evidence of exactly how much energy is moving through Jupiter's magnetic environment at any given moment. It stands as one clear signal, visible from a great distance, of a magnetic field being generated continuously by a fluid metal deep inside a planet, with no surface anywhere near where that light appears. For a long time, the standard picture of Jupiter's center involved a compact, rocky and icy core, dense and clearly separated from the layers of hydrogen and helium surrounding it, roughly the way an apple has one clear boundary between the fruit and the seed at its middle. Measurements made by the Juno spacecraft, using tiny shifts in its own trajectory to map the planet's gravity field in extraordinary detail, told a different story. Rather than a sharp, compact core, Jupiter appears to have what scientists now call a diluted or fuzzy core, heavy elements spread out gradually across a large fraction of the planet's radius, instead of concentrated into one small, dense region. One leading explanation is that a giant impact early in Jupiter's history stirred a once compact core into the surrounding hydrogen and helium, and it has never fully settled back out again. Whatever the cause, the practical result is that even at the very center of this planet, the place one might expect to finally find something solid and well-defined, the boundary keeps refusing to resolve into a clean edge. Jupiter gives off nearly twice as much energy as it receives from the Sun, a detail that surprised early observers who assumed a planet this far out should be cold. That extra warmth comes from within, generated mainly by the planet's own slow contraction. Jupiter is thought to be shrinking by only a few centimeters each year, a change too small to ever notice directly, but one that converts gravitational energy into heat as the whole structure settles very gradually inward on itself. Helium rain, deeper down, adds a further contribution, converting the energy of falling droplets into warmth, the same way water falling over a dam can, in principle, be made to release energy as it drops. Together, these processes mean that Jupiter behaves thermally a little like a very slow furnace, rather than a body reflecting sunlight, radiating away more heat than it takes in, and doing so continuously across a timescale of billions of years, with no sign of running out anytime soon. Because of this internal heat, temperature inside Jupiter never levels off the way it eventually does inside a rocky planet once you pass the mantle and approach a stable core. It keeps climbing, layer after layer, from the frigid haze at the cloud tops, through the liquid hydrogen ocean, through the metallic hydrogen deeper still, and on toward the diluted core, where estimates put the temperature at tens of thousands of degrees, hotter in places than the visible surface of the Sun itself. Pressure climbs alongside it, reaching many millions of times what Earth's atmosphere manages at sea level by the time the fall approaches the center. There is no point in this whole enormous structure, from the outermost wisp of ammonia cloud to whatever lies at the diluted heart of the planet, where the material changes from something you could fall through to something you could stand on. The flaw that every rocky world takes for granted simply never arrives here at any depth, under any amount of pressure. Step back out from the planet itself, and Jupiter's family of moons begins with 4 that have been known since telescopes were first pointed at the sky. In January 1610, using one of the earliest telescopes ever built, the astronomer Galileo Galilei noticed 4 small points of light shifting position around Jupiter from one night to the next, and correctly concluded they were orbiting the planet rather than sitting fixed among the stars. Those 4 moons, now grouped together as the Galilean moons in his honor, Io, Europa, Ganymede, and Callisto, were the first objects ever observed circling a body other than Earth, and the discovery overturned the assumption that everything in the sky had to orbit our own planet. Each of the 4 turned out, centuries later, to be its own small world with its own character. One scarred by constant volcanic eruptions, one wrapped in ice over a hidden ocean, one large enough to generate its own magnetic field, and one covered almost entirely in ancient craters. Together they orbit Jupiter, the way a miniature solar system orbits its star. 4 very different destinations circling one planet that itself has no destination at its center. Io, the innermost of the 4, is the most volcanically active body known anywhere in the solar system. Its surface constantly repaved by eruptions that can throw material hundreds of kilometers above the ground. That activity comes from a tug of war. Io is squeezed and flexed by Jupiter's gravity on one side and by the gravity of the other large moons on the other. A repeating stretch and release that heats its interior the way bending a piece of wire back and forth repeatedly warms the metal. Some of the material thrown up by Io's volcanoes escapes the moon's weak gravity entirely and drifts into space, where Jupiter's powerful magnetic field catches it, forming a donut-shaped ring of charged particles that circles the planet along Io's orbit. This ring, called a plasma torus, adds to the radiation trapped within the planet's magnetosphere. A small moon squeezed by gravity ends up shaping the behavior of the giant planet's magnetic field far beyond its own tiny size. Europa, the second of the 4, presents an almost featureless icy shell to any telescope, its surface crossed by long reddish cracks rather than craters or mountains, evidence of a crust young enough and active enough to erase most impact scars fairly quickly on a geological timescale. Beneath that ice, gravity measurements and the pattern of the cracks themselves point strongly toward a liquid water ocean, kept from freezing by the same tidal flexing that heats Io, though gentler here, and by whatever residual warmth rises from Europa's rocky interior below the water. That ocean is thought to hold more liquid water than every ocean on Earth combined, sealed beneath an ice shell many kilometers thick, entirely out of sight of any camera looking down from above. Europa is not the focus of tonight's journey, since our route runs through the giants themselves rather than their moons. But it is one of the more promising places among everything orbiting the outer planets where conditions might once have allowed something more than plain chemistry to occur. Ganymede, the third of the 4 Galilean moons, is the largest moon in the solar system, bigger across than the planet Mercury, though lighter, since much of its bulk is ice rather than rock. What sets Ganymede apart from every other moon known is a detail usually reserved for planets. It generates its own magnetic field, produced by motion within a layer of liquid iron somewhere in its interior, the same basic mechanism that produces Jupiter's own far larger field. That field is strong enough to carve out a small magnetic bubble of its own, nested inside Jupiter's much larger one, and it produces a faint glow at Ganymede's own poles that telescopes have photographed from Earth by watching how the Moon's thin oxygen atmosphere responds. No other moon anywhere in the solar system is known to do this. Ganymede sits, in a sense, as a small demonstration of the same physics playing out on a vastly larger scale just beyond it. Proof that a magnetic field generated by internal motion is not something only the giant planet itself is capable of producing. Callisto, the outermost and last of the 4 Galilean moons, is essentially a fossil, a body whose icy surface has barely changed since the earliest era of the solar system and is now covered almost completely in overlapping impact craters, more of them per square kilometer than almost anywhere else surveyed by spacecraft. Unlike Io, Europa, and Ganymede, Callisto sits far enough from Jupiter that the tidal flexing responsible for their heat barely affects it, leaving its interior cold and its geology largely frozen in place for billions of years. That stillness makes Callisto something like a record, a surface where scientists can read the history of impacts across the outer solar system, the way a well-preserved rock face can be read for the history of a cliff. Even here, though, faint hints of a subsurface layer of salty water have shown up in magnetic measurements, suggesting that even the quietest and most heavily battered of Jupiter's 4 large moons may not be entirely solid all the way through. 4 moons, 4 different stories, all of them circling a planet that offers no story of a flaw at its own center. Jupiter also has rings, though they are so faint that they went undetected until the Voyager 1 spacecraft photographed a thin, dusty band while passing through the system in 1979. Unlike the bright, broad rings that make Saturn instantly recognizable, Jupiter's rings are built from fine, dark dust, constantly kicked up by tiny meteoroid impacts, striking its 4 small inner moons. And they reflect so little sunlight that they are essentially invisible from Earth without a spacecraft looking back toward the Sun from the shadowed side of the planet. The system has a main ring, a faint inner halo, puffed up above and below the main plane by the pull of Jupiter's magnetic field on the smallest dust grains, and 2 even fainter outer rings, named for the tiny moons that supply their material. None of it comes close to Saturn's scale or brightness, but its presence shows that ring systems are not unique to one planet in this family. Wherever there is a giant planet with small moons nearby, it seems, some amount of dust tends to gather into a thin disk around it. In March 1993, astronomers Caroline and Eugene Shoemaker, working with David Levy, discovered something unusual through a telescope. Not one comet, but a chain of at least 20 separate fragments, strung out in a line like beads, orbiting not the Sun directly, but Jupiter itself. Calculations quickly showed that the original comet, whole and single, had passed extremely close to Jupiter some 8 months earlier, close enough that the planet's gravity had torn it apart before anyone had spotted it. What had once been one icy body was now a scattered train of pieces, each a few hundred meters to a couple of kilometers across, following an orbit that would bring them back toward Jupiter again about 16 months later. It was, and remains, the first time astronomers had ever caught a comet in the act of breaking apart around another planet, and it gave researchers unusually precise advance warning of an even stranger event still to come. one that nobody watching the sky had ever had the chance to prepare for before. What tore that comet apart has a name. The Roche limit. The distance from a large body inside which its gravity pulls harder on the near side of a smaller object than on the far side, stretching that object until its own gravity can no longer hold it together. Every planet has such a limit, a boundary that shrinks the denser and stronger the smaller body is. But for a loosely packed comet nucleus, held together by little more than weak ice and dust cohesion, the limit can sit a considerable distance out, well clear of the planet's visible clouds. Cross inside that limit, and an object faces a simple choice. It must either be dense and strong enough to resist the stretching, or it comes apart into pieces, the way the comet destined for Jupiter did in 1992. The same physics, it turns out, governs far more than one unlucky comet. And later tonight, once the journey has crossed over to Saturn, this same limit reappears in a much larger and much more visible form, wrapped in ice rather than scattered as fragments. In July 1994, the fragments returned, and over the course of 6 days, each of them struck Jupiter's atmosphere in turn, plunging in at roughly 60 kilometers a second and releasing energy on impact that in several cases outmatched every explosion in recorded human history put together many times over. Telescopes around the world, and for the first time in history a spacecraft already in position to watch, recorded dark, bruise-like marks blooming in the clouds after each strike, some almost as wide across as Earth itself. It was the first time humanity had ever directly observed a collision between two bodies in the solar system, rather than finding the leftover crater afterward, the way earlier impacts on the Moon or Mars had to be studied. The dark scars lingered in Jupiter's atmosphere for months, slowly stretched and eventually smeared apart by the same restless winds that shape every other feature in those clouds, until nothing remained to mark where 21 pieces of comet had struck one after another. A collision violent enough to be seen from Earth left no permanent record here, only clouds folding back over the place where it happened. The first spacecraft ever to reach Jupiter were Pioneer 10 and Pioneer 11, launched in 1972 and 1973. Simple by later standards, but the first machines to cross the asteroid belt successfully and return close-up data from the giant planets waiting beyond it. Pioneer 10 flew past Jupiter in December 1973, sending back the first detailed images of its clouds and confirming that the planet's radiation environment was far harsher than engineers had expected. Information that shaped the design of every mission that followed. Pioneer 11 followed a year later, using Jupiter's gravity to bend its path onward towards Saturn, arriving there in 1979 and becoming the first spacecraft ever to visit that planet as well. Both probes carried a small engraved plaque showing the shape of a human figure and the location of Earth, a message aimed less at Jupiter itself than at whatever might one day find the spacecraft long after it had left the solar system entirely, still drifting outward, having long since finished the only close encounter it would ever have with a planet. 5 years after Pioneer, the two Voyager spacecraft arrived at Jupiter in 1979, carrying far more capable cameras and instruments, and the images they returned changed. How Jupiter was understood almost overnight. Voyager 1 captured the first clear pictures of active volcanic plumes rising from Io, the first confirmation that a moon other than Earth's own had ongoing eruptions happening in real time as the spacecraft watched. Voyager 2, following a few months later, refined measurements of the planet's faint rings and photographed the swirling structure of its clouds in enough detail to track individual storms over the course of days. Between them, the two spacecraft also mapped Jupiter's 4 large moons, closely enough to plan the more detailed missions that would follow decades later, and confirmed details of the planet's enormous magnetic field that had only been guessed at before. Neither Voyager stayed at Jupiter for long. Both used the planet's gravity as a slingshot, bending their paths onward and outward, carrying what they had learned towards Saturn and eventually out past the edge of the solar system altogether. The Galileo spacecraft, which released the atmospheric probe described earlier, arrived at Jupiter in December 1995 and then remained in orbit for nearly 8 years, becoming the first mission to study the planet and its moons over an extended period rather than during a brief flyby. In that time, it mapped the icy shell of Europa in close detail, watched Io's volcanoes erupt and fade, and confirmed strong evidence for Ganymede's own magnetic field. By 2003, the spacecraft was running low on fuel, and engineers faced a decision: leave it drifting, with a small risk it might eventually crash uncontrolled into Europa and contaminate a moon that might harbor a hidden ocean, or send it somewhere it could do no harm. They chose the second option, deliberately steering Galileo into Jupiter's atmosphere on the 21st of September that year, where it burned and was crushed within minutes, the same fate that had met its own smaller probe 8 years earlier. A mission that spent years learning what it could about a world with no flaw was, in the end, sent to disappear into that same endless fall on purpose. The most recent spacecraft to reach Jupiter is Juno, which arrived in July 2016 and spent years orbiting the planet in a long, looping path, swinging close over the poles every few weeks before retreating far out again to avoid lingering too long in the worst of the radiation. Juno carries JunoCam, a camera added mainly for public outreach, whose images of the planet's turbulent poles have become some of the most striking pictures ever taken of another world. Its main instruments measure the planet's gravity and magnetic field with extraordinary precision, work that produced the discovery of the diluted core mentioned earlier and revealed that the magnetic field itself is far lumpier and less tidy than scientists had assumed before the mission began. Juno has already outlasted its original planned lifetime several times over, and each extension has added more detail to a picture of Jupiter that keeps turning out to be stranger and less orderly, the deeper the spacecraft's instruments manage to see. Among Juno's more unexpected discoveries is the arrangement of storms sitting directly at Jupiter's poles, a region no earlier spacecraft had ever photographed clearly because none had flown a path steep enough to look straight down on it. At the North Pole, images revealed 8 enormous cyclones, arranged around a ninth at the very center, each one a few thousand kilometers across, packed closely enough together that their edges nearly touch. The South Pole shows a similar but not identical pattern, 6 large cyclones circling a central one instead of 8, evidence that whatever process holds this arrangement in place is stable but not perfectly symmetrical between the two hemispheres. These storms have persisted, largely unchanged in arrangement, across the years Juno spent observing them, jostling against their neighbors without merging into a single storm or drifting apart. Nobody had predicted or fully explained this standing pattern before the spacecraft's cameras first looked down at the pole and found it staring back with a ring of storms instead of the smoother swirl seen everywhere else on the planet. Jupiter's gravity reaches out well beyond its own moons and shapes the asteroid belt lying between Mars and Jupiter's own orbit, carving gaps in the distribution of asteroids at certain distances from the Sun, called Kirkwood gaps, after the astronomer who first identified the pattern in the 19th century. Asteroids that happen to orbit at those particular distances complete a whole number ratio of orbits for every orbit Jupiter makes, a resonance that repeatedly tugs them in the same direction at the same point in their path. And over enough repetitions, that tug either flings them onto a new orbit or rejects them from the belt altogether. The result, visible in any plot of asteroid orbits, is a set of conspicuously empty bands running through the belt, regions where almost nothing lingers for long, even though the neighboring bands are comparatively crowded. Few forms of influence are stranger for a planet to have. It reaches across the emptiness between orbits, not through any physical contact, but purely through the steady, repeated pull of gravity, acting on exactly the right rhythm to matter. Sharing Jupiter's orbit, rather than sitting in the belt closer to Mars, are two large swarms of asteroids called the Trojans. One gathered roughly 60 degrees ahead of the planet, and the other roughly 60 degrees behind it. These positions, called Lagrange points, are places where the combined gravity of the Sun and Jupiter, together with the motion of an orbiting body, balances out in a way that lets smaller objects sit there stably for extremely long stretches of time without drifting away. Thousands of Trojan asteroids have been catalogued so far, ranging from small chunks only a few hundred meters across up to bodies more than 100 kilometers wide, and current estimates suggest the true population may rival the asteroid belt itself in number. Far from being an isolated planet with a simple ring of moons around it, Jupiter turns out to be surrounded by an entire extended entourage of smaller bodies. Some orbiting close, some sharing its orbit at a careful distance. All of them arranged by the same gravity that, closer in, never quite manages to hold together a floor at the center. Beyond the four large Galilean moons, Jupiter has an enormous retinue of much smaller ones, more than 100 confirmed at last count, and new ones still turning up as telescopes and survey techniques improve. Many of these smaller moons orbit far out from the planet, on paths tilted steeply relative to Jupiter's equator, and, in a good number of cases, running backward compared to the planet's own rotation. A strong hint that they were not born alongside Jupiter at all, but were captured later, drifting close enough for its gravity to catch and hold them permanently. Most are irregular in shape rather than rounded, too small for their own gravity to pull them into a sphere. And many are thought to be fragments of larger bodies that broke apart after colliding with one another sometime in the distant past. Cataloging them all has become an ongoing project rather than a finished list, and each newly confirmed moon adds one more small, cold, captured wanderer to the crowd already circling a planet whose own interior refuses to settle into anything as tidy as a single, well-defined shape. Long before any spacecraft reached Jupiter, astronomers on Earth had already noticed something odd about it, using nothing more than radio telescopes. In 1955, two researchers scanning the sky for unrelated reasons picked up bursts of radio static that turned out to be coming from Jupiter itself, an early and completely unexpected clue that something powerful was happening around the planet beyond what any visible light telescope could show. Those radio bursts, later traced to the interaction between Jupiter's magnetic field and the moon Io moving through it, are strong enough in certain frequency ranges that Jupiter is, after the Sun, the loudest radio source among the planets as seen from Earth. Amateur radio enthusiasts with fairly simple homemade antennas can still pick up these signals today, decades after their first accidental discovery. A reminder that some of what makes this planet so unusual was detectable from our own back gardens long before a single spacecraft had ever left Earth's orbit to go and look more closely. Because metallic hydrogen is so difficult to produce, physicists on Earth have spent decades trying to recreate even a tiny sample of it under laboratory conditions, using devices such as diamond anvils that squeeze microscopic amounts of hydrogen between two hardened diamond tips, or brief pulses from powerful lasers that compress a sample for a fraction of a second. Some experiments have reported brief glimpses of hydrogen behaving like a metal, showing sudden changes in how it reflects light. Though the results remain difficult to reproduce consistently and are still debated within the field. None of these experiments can sustain the pressure for more than an instant, because the equipment capable of generating it is destroyed in the same moment the measurement is taken. Inside Jupiter, by contrast, those same pressures are simply the ordinary condition at a certain depth, sustained not for an instant, but for the entire age of the planet, without any machinery at all, just the steady weight of everything above, pressing down without pause on everything below it. Some researchers, studying how the solar system's planets ended up arranged the way they are today, have proposed that Jupiter did not stay put during its early history. According to one hypothesis, sometimes called the Grand Tack, Jupiter may have migrated inward toward the Sun not long after it formed, before being pulled back outward again by a gravitational tug-of-war with Saturn, once that planet had also grown large enough to matter. If something like this happened, it could help explain several otherwise puzzling features of the inner solar system, including why Mars ended up smaller than earlier models predicted, and why the asteroid belt looks the way it does today, gently stirred rather than left completely undisturbed. This remains one hypothesis among several, rather than a settled account, and different research groups still disagree about the details or whether the migration happened at all. What is not in dispute is that a planet this massive, wherever exactly it has spent its history, has never been a quiet bystander to the wider solar system's formation. Io, Europa, and Ganymede are locked together in a precise rhythm called an orbital resonance. For every time Ganymede completes one orbit of Jupiter, Europa completes almost exactly 2, and Io 4. This repeating relationship means the three moons regularly line up in the same relative positions. And each time they do, their combined gravity gives Io's orbit a slight tug away from a perfect circle, keeping it very slightly stretched rather than allowing it to settle into a calmer, rounder path. That stretching is precisely what flexes Io's interior and drives its extraordinary volcanic activity, and, to a lesser extent, it keeps Europa's ice shell warmer than it would otherwise be far from the Sun. Ganymede, farther out and less strongly affected, still feels a small amount of the same tug. This resonance has likely persisted for a very long stretch of the solar system's history, a kind of gravitational clockwork running among three moons, converting the ordinary business of orbiting a planet into a steady internal heat source for at least two of them. Because Jupiter has no solid surface to measure from, scientists who need a reference point for altitude, pressure, or wind speed have agreed on a convention rather than a physical landmark. The level in the atmosphere where pressure equals 1 bar, roughly what Earth's atmosphere exerts at sea level, is defined as 0 altitude for the purposes of comparison. Everything above that level counts as a positive altitude, and everything below it counts as negative, even though nothing marks that boundary in any way a falling object would notice as it passed through. It is a little like agreeing to measure the depth of an ocean with no floor by picking an arbitrary line partway down and calling it 0, useful for keeping charts and comparisons consistent, but not a claim that anything physical actually changes at that exact point. Scientists studying Jupiter's weather, storms and winds rely on this invented 0 constantly, a small piece of bookkeeping built specifically to cope with a planet that offers absolutely nothing solid to measure from instead. Some of the fastest sustained winds recorded on any planet blow through Jupiter's atmosphere, with certain streams of cloud moving at several hundred kilometers an hour relative to their neighbors, driven by the planet's own rapid spin and by heat rising steadily from the warmer layers underneath. These streams do not follow the pattern familiar from Earth's weather, where storms form, move, and dissipate against continents and oceans within days. Here, with no landmass anywhere to slow anything down or break a current apart, the same flows can persist for years or decades, essentially unchanged, since there is nothing in their path capable of interrupting them. Energy that would be absorbed by mountains, forests, or open water on a rocky planet keeps circulating on Jupiter, passed from one layer of cloud to another, instead of being lost to the ground. The same underlying truth runs through this entire planet. Without a surface anywhere to act as a brake, motion here tends to continue rather than settle. At the very top of the atmosphere, the numbers tell an almost misleading story. Cloud top temperatures average somewhere around -145 degrees Celsius, cold enough to freeze nearly anything found on Earth's surface solid within moments. A visitor arriving from outside and measuring only that first reading might conclude Jupiter is a bitterly cold world through and through. And for the outermost few hundred kilometers, that conclusion would even be correct. Continue downward, though, and that impression reverses completely within a surprisingly short distance. The temperature climbing past values found at Earth's surface within the first 100 kilometers or so of descent, and continuing to climb steeply after that with no sign of leveling off. Nowhere else in the solar system does a single planet's temperature range swing this dramatically across one continuous atmosphere. From a cold, able to freeze carbon dioxide solid at the top, to a heat exceeding the surface of the Sun much further down, all of it connected by the same unbroken fall, with nothing marking the change from one extreme to the other. Jupiter's axis is tilted only a little over 3 degrees from vertical relative to its orbit, one of the smallest tilts of any planet in the solar system, meaning it has essentially no seasons in the way Earth or Mars experience them. Where Earth's 23-degree tilt swings each hemisphere toward and away from direct sunlight across the year, producing summer and winter, Jupiter's clouds receive almost the same angle of sunlight at every point in its long 12-year orbit, with any changes driven far more by the planet's own weather than by anything the Sun is doing overhead. This steadiness makes Jupiter's cloud patterns somewhat easier to model over the long term than they might otherwise be, since researchers do not have to account for a shifting angle of incoming sunlight the way they would on a more tilted world. Even here, though, steadiness in the tilt does not translate into calm weather. This is still a planet capable of storms lasting centuries, driven from within rather than by anything so simple as the changing of seasons overhead. Beyond visible light and radio noise, Jupiter also produces its own bursts of X-rays, concentrated at the poles and pulsing on a rhythm of roughly every 27 minutes. A pattern first fully explained only in 2021, after examining years of data from an orbiting X-ray telescope. Researchers traced the cause to charged particles trapped in the planet's magnetic field, briefly caught and accelerated along particular field lines by a kind of electromagnetic wave, then funneled down toward the poles, where they strike the upper atmosphere and release their energy as X-ray light. It took decades of observation to work out a mechanism this specific, because the pulses are faint, irregular in exact timing, and buried within a magnetic environment already crowded with radio noise and trapped radiation. The discovery added another item to the long list of energy Jupiter radiates outward in forms invisible to the naked eye, on top of the heat and the radio bursts. Jupiter's gravity has such a strong influence on the orbits of comets passing through the outer solar system that an entire category of them, known as Jupiter family comets, is named for the planet's effect on their paths. These are comets whose orbits have been reshaped by repeated close encounters with Jupiter over many passages, pulled from far wider, longer paths into tighter orbits that bring them back through the inner solar system every few years rather than every few centuries. Some end up flung outward instead, ejected onto much longer orbits or out of the solar system altogether, depending on the exact geometry of each encounter. Jupiter's influence here works in both directions at once, occasionally directing objects toward the inner solar system just as it sometimes draws potential impactors in for itself, as the events of 1994 demonstrated in the most direct way possible. Nothing about this influence is deliberate in any sense, only the steady application of a very large mass's gravity on anything that happens to wander close enough to feel it. The faintest and outermost parts of Jupiter's ring system are called the gossamer rings, named for how thin and translucent they appear, even by the standards of a ring system already far too dim to see without a spacecraft looking back toward the Sun. These outer rings are supplied by dust knocked loose from two small inner moons, Amalthea and Thebe, struck constantly by tiny meteoroids, too small to see individually, but numerous enough over time to keep a steady haze of particles drifting in roughly the same orbits as the moons that shed them. Because the dust grains are so small, sunlight and the planet's own magnetic field push and pull them constantly, spreading the rings out into a puffed, cloud-like shape rather than the flat, sharply defined disk found around Saturn. Nothing here will ever gather itself into anything larger. The particles are too small, too scattered, and too thoroughly stirred by outside forces ever to settle down into a single body, remaining instead a thin, restless haze circling a planet that, deeper down, has trouble settling into anything solid either. Surviving long enough near Jupiter to gather useful data required an unusual piece of engineering aboard the Juno spacecraft. A vault built from titanium plates roughly a centimeter thick, enclosing the spacecraft's main electronics inside a small armored box, rather than leaving them exposed the way most spacecraft components are. Even with that shielding, the intense radiation trapped in Jupiter's magnetosphere is expected to degrade the vault's protection gradually over the course of the mission. One reason engineers designed Juno's orbit to swing in close only briefly before retreating to a safer distance each time, rather than settling into a closer, steadier path, the way missions around calmer planets often do. Without this kind of deliberate protection, ordinary electronics would fail within hours of arriving this close to Jupiter. Overwhelmed by charged particles, the planet's own magnetic field has spent billions of years gathering and accelerating. Nothing says more about the power of that field than an entire vault of titanium, built and flown across hundreds of millions of kilometers, purely to buy a spacecraft a little more time before the planet's magnetism finds a way to reach it anyway. A single one of Jupiter's smaller storms, one of the countless white ovals that come and go across its clouds each decade, can already rival the size of Earth's largest hurricanes, and the largest and longest-lived storms on the planet dwarf anything a hurricane on Earth ever produces. Part of the reason lies in what stops a storm from growing in the first place. Earth's hurricanes eventually run into cooler water, dry land, or wind shear from a passing weather system, any of which can weaken or break the storm apart within days or weeks. Jupiter's storms encounter none of that, only more of the same restless atmosphere in every direction. So, a storm that begins large has comparatively little standing in the way of continuing largely undisturbed. Some of the smaller, shorter-lived storms merge with one another when their paths happen to cross, occasionally producing something briefly larger before it settles back down. A process astronomers have tracked directly through repeated photographs taken years apart, watching two separate storms slowly close the distance between them until only one remained. Jupiter has been watched and recorded for longer than almost anything else in the sky, easily visible to the naked eye as one of the brightest points of light after the Moon and Venus. And ancient Babylonian astronomers were already tracking its position against the stars and predicting its movement with reasonable accuracy more than 2,500 years ago. The Romans eventually named it after the king of their gods, a fitting choice for the planet that outshines every star in the night sky, and that name has stuck through every language that borrowed it since. For most of human history, everyone who ever looked up and noticed Jupiter's steady, bright presence had no way of knowing that the point of light they were tracking across the night sky was, up close, a bottomless ocean of gas and metal, with weather systems large enough to swallow entire worlds. Averaged across its whole volume, Jupiter's density works out to a little under 1 1/3 times that of water, a modest figure for a planet of such enormous mass, and a reminder that averaging tells very little about a world built in layers this different from one another. At the cloud tops, the gas is thinner than Earth's own air. At the center, inside the diluted core, densities are thought to rival or exceed that of the densest metal found naturally on Earth. A single average number smooths all of that into one figure, useful for certain kinds of comparison, but almost meaningless as a description of what conditions are actually like at any specific depth. It is a little like averaging the temperature of a bath filled with both ice and boiling water, and reporting the result as lukewarm. Technically accurate, and completely unhelpful for anyone trying to understand what they would actually experience reaching into it at any particular point. Not every spacecraft that photographed Jupiter closely was built to study Jupiter at all. In December 2000, on its way towards Saturn, the Cassini spacecraft passed close enough to Jupiter to spend several weeks taking pictures, and because its cameras were more capable than anything carried by Voyager 2 decades earlier, the resulting images became, for a time, the most detailed global portrait of the planet ever assembled, stitched together from a mosaic of separate frames into a single continuous view of the clouds. Cassini's instruments also studied Jupiter's magnetosphere in passing, comparing notes with what the earlier missions had found, and helping researchers understand how such an enormous magnetic environment changes over the years between visits. For a spacecraft with somewhere else entirely to be, that was a brief and thorough second look at Jupiter, borrowing the planet's gravity for a boost toward its real destination, while making the most of the weeks spent nearby. Jupiter's moons are currently the target of 2 further spacecraft already on their way. The European Space Agency's JUICE mission, launched in 2023, is traveling toward Jupiter to study Ganymede, Callisto, and Europa in detail, and is expected eventually to become the first spacecraft ever to orbit a moon other than our own, once it settles into orbit around Ganymede rather than around Jupiter itself. NASA's Europa Clipper, launched in 2024, is headed specifically for repeated close flybys of Europa, using instruments built to measure the thickness of its ice shell and search for any sign of the ocean beneath, making contact with the surface above it. Neither spacecraft is expected to arrive for several more years, since the journey out to Jupiter takes the better part of a decade, even with gravity assists along the way from other planets. When they do arrive, both will add to a growing catalogue of exploration built layer upon layer since Pioneer's first cautious flyby, each mission answering a few of the questions the last one left open. Between the main asteroid belt and Jupiter's own orbit sits a smaller, less well-known group of asteroids called the Hildas, held in place by a different resonance from either the Trojans or the gaps named after Kirkwood. Each Hilda completes exactly 3 orbits of the Sun for every 2 orbits Jupiter completes, a relationship that traces out a rough triangular pattern relative to Jupiter's position over time, rather than a simple circle, and that keeps the group stable across an enormous span of time, despite sitting closer to Jupiter's own gravity than most of the main asteroid belt does. Several thousand Hilda asteroids have been catalogued, and their unusual triangular collective path has made them useful test cases for understanding how orbital resonances shape the structure of small body populations more generally. Not just around Jupiter, but around other planetary systems studied by telescopes far beyond our own. Much of the debris scattered around this solar system has, in one way or another, been organized into place by the same steady pull, radiating outward from the one planet nothing nearby can ignore. Amalthea, one of the small moons supplying material to Jupiter's faint gossamer rings, radiates noticeably more heat than sunlight alone, striking its dark, reddish surface should produce. A small anomaly first spotted by Voyager and later measured in more detail by Galileo. One possible explanation is that Amalthea, orbiting well inside the region where Io's volcanic material and Jupiter's radiation both concentrate, absorbs and re-emits energy from its surroundings, rather than generating heat internally the way Io itself does through tidal flexing. Amalthea also orbits closer to Jupiter than any of the 4 large Galilean moons, completing a full circuit in well under a single Earth day. Close enough that an observer standing on its surface, if such a thing were possible, would see Jupiter hanging almost motionless overhead and filling much of the sky, its cloud features drifting slowly past. A small, irregular moon, a couple of 100 kilometers across, has a quiet puzzle of its own attached to it. Another loose thread in a system that keeps producing more of them the closer anyone looks. Although Jupiter holds less than 1/1000th of the mass contained in the Sun, it carries a substantial share of the solar system's total angular momentum, the measure of how much everything in the system is spinning and orbiting combined. Simply because it sits so far out and orbits with such enormous momentum built into its wide, slow circuit. The Sun, despite holding more than 99% of all the mass in the solar system, accounts for only a small fraction of its total angular momentum, most of which instead belongs to the orbits of the planets, and Jupiter alone contributes the largest single share of anything besides the Sun. This imbalance has puzzled astronomers studying how solar systems form in general, since the simplest models of a collapsing cloud of gas would predict the central star ending up with far more of the spin than the Sun actually kept. Jupiter's outsized share of the system's motion is one of the clues researchers use when testing theories about exactly how planets and stars divide up the material and momentum of the cloud they were both born from. Long before any spacecraft carried instruments close enough to sample Jupiter's atmosphere directly, astronomers had already worked out some of its properties using a much older and more patient technique. Watching Jupiter pass in front of a distant star and timing exactly how the star's light dimmed and brightened again as the planet's atmosphere slid across it. The way starlight bends and fades while filtering through those outer layers reveals information about temperature, pressure, and density at the altitudes involved, all worked out purely from timing and brightness measurements taken from telescopes on Earth, without ever sending anything close to the planet itself. Several such occultations, carefully observed and timed across the 20th century, gave scientists their first real estimates of conditions in Jupiter's upper atmosphere, well before Pioneer or Voyager confirmed and refined the numbers directly. A great deal of what is known about even the most distant and largest planets was pieced together patiently from Earth, using nothing more exotic than a telescope, a clock, and the fortunate timing of a star passing briefly behind a very large planet. Among Jupiter's many small outer moons, astronomers have noticed that several cluster into loose groups sharing similar orbital distances, tilts, and directions of travel, evidence that each group likely began as a single, larger captured body that later broke apart after a collision with another object passing through the same region. Rather than 100-odd unrelated captured objects, the outer moon system looks more like a handful of original captures, perhaps a dozen or so, each one subsequently shattered into a scattered family of fragments, still following roughly the orbit of their now vanished parent. Untangling exactly how many original bodies these families trace back to, and when each collision happened, has become an active area of research, pieced together from precise orbital measurements taken by ground-based telescopes over years and even decades of tracking. Even the outermost, least significant seeming members of Jupiter's moon system carry a kind of fossil record of their own violent history, written into the shape and tilt of their orbits, rather than into anything visible on their surfaces. Jupiter's family of small, irregular outer moons includes several with retrograde orbits, grouped loosely under names drawn from the lovers and descendants of Zeus, distinct from the inner prograde moons named after figures closer to Jupiter in the same Greek and Roman tradition. Astronomers adopted this naming split deliberately once the outer moon population grew large enough to need some organizing principle, using orbital direction as the simplest available marker for grouping newly discovered bodies before their exact origins were understood in any detail. Many of these outer moons are only a few kilometers across, discovered decades after the first 4 Galilean moons, using wide-field cameras and patient, repeated imaging of the same patch of sky, rather than a single, close spacecraft flyby. Their small size and great distance make them difficult to study in any detail beyond a basic orbit, leaving most of them little more than a name, a size estimate, and a confirmed but distant path circling a planet, far better understood than these faint, scattered outer companions ever will be. Ganymede's icy surface is not uniform, split roughly between older, darker terrain, thickly covered in craters, and younger, brighter terrain crossed by long parallel grooves and ridges, evidence of past tectonic activity, stretching and resurfacing the ice in some regions, while leaving others essentially untouched for billions of years. Exactly what drove that resurfacing remains debated, though tidal flexing from Jupiter, similar in kind to what shapes Io and Europa, though gentler here, is thought to have played a role at some point in Ganymede's history, even if the moon has since settled into a quieter, less active state than its 2 inner neighbors. Spacecraft images have traced individual grooved bands for hundreds of kilometers across the surface, some crossing directly over older, cratered terrain, in a way that lets scientists work out roughly which regions formed first and which came later, reading the moon's geological history the way a page of overlapping handwriting can sometimes still be read layer by layer. Even the largest moon in the solar system, then, carries its own quieter record of change written into its ice. 2 very small moons, Metis and Adrastea, orbit closer to Jupiter than any others, circling within the main ring itself rather than outside it, close enough that a full trip around the planet takes each of them less time than a single Earth day. Their gravity is thought to help confine the outer edge of Jupiter's main ring, gently shepherding stray dust particles the way slightly larger shepherd moons do around Saturn's much brighter rings, keeping the boundary reasonably sharp instead of letting it blur gradually outward over time. Both moons are irregular lumps of rock, only a few tens of kilometers across, discovered only once spacecraft cameras were finally capable of picking out something so small and so close to the glare of Jupiter's clouds beneath them. Sitting this deep inside Jupiter's gravity and radiation environment, neither moon has an easy existence, constantly showered with charged particles and dust impacts, contributing in its own small way to the same restless ring of debris that circles a planet with no floor of its own to settle onto. Saturn orbits nearly twice as far from the Sun as Jupiter does, taking almost 29.5 years to complete a single circuit. Distant enough that sunlight reaching its cloud tops is fainter still than the pale light Jupiter receives, closer to a deep dusk than to any ordinary daylight. Despite that distance, Saturn is unmistakable, even through a small telescope from a back garden. Not for its clouds, which are paler and less dramatic than Jupiter's, but for the wide, flat rings that circle it and catch sunlight at an angle no other planet's rings manage to match. Saturn is the second largest planet in the solar system, smaller than Jupiter, but still large enough that more than 700 Earths could fit inside its volume. A giant world by any ordinary measure, simply overshadowed in the popular imagination by an even larger neighbor. Beneath that pale, unremarkable-looking cloud deck, though, Saturn hides almost exactly the same kind of bottomless structure Jupiter does, and the same descent runs downward a second time, through gas that thickens, through metal made of hydrogen, and toward a core that stays just as hard to pin down. Saturn is built from the same basic ingredients as Jupiter, mostly hydrogen with a smaller share of helium mixed through it, but the exact proportions differ in a way that turned out to be an important clue about what happens deep inside both planets. Measurements taken by spacecraft show Saturn's outer atmosphere noticeably poorer in helium relative to hydrogen than the Sun itself is, an even larger shortfall than the one already noticed at Jupiter. The leading explanation is the same helium rain described earlier in Jupiter's own descent, except that inside Saturn, the process appears to run more efficiently, sinking a larger share of the planet's original helium down out of the outer layers and toward the interior over billions of years. It has been raining helium for longer, or more heavily, or under conditions that favor the process more strongly, leaving its outer atmosphere measurably thinner in helium than its larger neighbors, a difference written directly into the chemistry of the clouds we can see from here. Saturn's mass comes to only about a third of Jupiter's, yet it still outweighs every other planet in the solar system besides Jupiter itself, more than 90 times the mass of Earth, packed into a body that manages, despite that bulk, to have the lowest average density of any planet in the solar system. That low average density does not mean Saturn is light in any ordinary sense, only that its enormous volume is filled overwhelmingly with the lightest possible elements rather than rock or metal. The same hydrogen and helium found throughout Jupiter, but arranged around a smaller core and under somewhat lower pressure at any given depth. A world this size, built almost entirely from the lightest material there is, behaves in ways rocky planets cannot. From the way it responds to the gravity of its own moons, down to the way pressure and temperature increase together the deeper any point inside it happens to sit. Where Jupiter's clouds show sharp, contrasting bands of cream and rust, Saturn's are wrapped almost uniformly in a pale gold, sometimes described as butterscotch, with far less visible contrast between one latitude and the next when viewed through an ordinary telescope. Part of the reason is a high, thin haze sitting above the main cloud deck, formed as sunlight breaks apart simple hydrocarbon molecules and stitches them into a smog that partly veils the more colorful chemistry churning underneath, muting Saturn's appearance the way a light fog can soften the colors of a landscape without hiding its shape entirely. Only when spacecraft cameras look in infrared light, seeing past that haze, does Saturn's cloud structure reveal storms, currents, and turbulence every bit as complex as anything found on Jupiter, hidden from ordinary sight by an extra veil that Jupiter's atmosphere does not share in the same way. The calm, pale face Saturn shows from a distance turns out to be a matter of what is sitting on top, not a sign of anything calmer happening underneath. Just as with Jupiter, there is no altitude inside Saturn's atmosphere where gas gives way cleanly to liquid. Descend far enough below that pale haze, and the same gradual thickening takes over. Pressure climbing steadily until the hydrogen around a falling object behaves as a dense fluid rather than a gas, without ever crossing a boundary sharp enough to call a surface. Because Saturn is somewhat less massive than Jupiter, the pressures involved at any given depth are a little lower, which pushes each of these transitions slightly further down inside the planet than the equivalent stage would sit inside Jupiter, though the overall sequence of layers is otherwise remarkably similar. A probe falling into Saturn would experience much the same story the Galileo probe already told at Jupiter. Cold at first, thickening steadily, warming gradually, and eventually crushed long before reaching anything that could be called a floor, only somewhat later in the fall than it would have happened at the larger planet next door. Saturn radiates roughly 2.5 times more energy than it receives from the Sun, a larger ratio than Jupiter manages despite Saturn's smaller size. And the extra helium rain, already discussed, is a major part of why. Because helium separates out of Saturn's hydrogen more efficiently, more gravitational energy is released as those droplets sink deeper into the planet, adding a substantial source of heat beyond whatever comes from Saturn's own slow gravitational contraction alone. Some models suggest that gravitational contraction by itself cannot fully account for how warm Saturn actually is, and that the extra contribution from helium rain is necessary to make the numbers work out. A rare case where a planet's internal chemistry directly explains an otherwise puzzling piece of its measured heat output. One thread connects the two planets here. The same basic process, helium sinking through hydrogen, running at a different pace in each of them, and leaving a different, individually measurable signature in how much heat each one gives off into the surrounding dark. Saturn also has a layer of metallic hydrogen deep inside it, formed the same way Jupiter's is, through pressure so extreme that hydrogen's electrons stop belonging to individual atoms and instead move freely enough to conduct electricity like an ordinary metal. Because Saturn is less massive, the pressure needed to reach that state is found considerably deeper relative to the size of the whole planet than it is inside Jupiter, meaning proportionally more of Saturn's interior sits in the earlier liquid hydrogen stage before the metallic layer even begins. Some researchers have proposed that the transition inside Saturn may not be as sharp as it is thought to be inside Jupiter, with a more gradual zone where hydrogen is only partially metallic before becoming fully so further down, an idea still being tested against detailed measurements of Saturn's gravity and magnetic field. Whatever the precise shape of that transition turns out to be, the basic outcome is the same as at Jupiter, an ocean of conductive metal made from the simplest possible element forming somewhere within the deeper half of the planet. Saturn's magnetic field holds a genuine puzzle that Jupiter's does not. It is almost perfectly aligned with the planet's own axis of rotation, tilted by less than 1 degree, an alignment so close that standard dynamo theory says it should be essentially impossible to sustain over long periods of time. The equations describing how a magnetic field is generated by a moving conductive fluid generally predict that a field this well aligned should decay away relatively quickly, since the process that sustains a dynamo usually depends on some degree of tilt and asymmetry to keep working. Saturn's field has nonetheless stayed close to this near-perfect alignment for as long as it has been measured, across the entire span from ground-based observations decades ago through to the Cassini spacecraft's detailed readings taken from within the planet's own magnetic environment during its final orbits. Several explanations have been proposed, most involving a thin, stable layer somewhere in the transition between metallic and non-metallic hydrogen that smooths out any tilt before it becomes visible from outside. But no single explanation has yet been fully confirmed, leaving the alignment as one of Saturn's more unresolved mysteries. Where Jupiter's magnetosphere is fed largely by material thrown up from volcanic Io, Saturn's is fed by a much gentler source, the moon Enceladus, whose icy geysers constantly spray fine water vapor and ice particles into space near Saturn's orbit. Saturn's magnetic field catches a portion of that material, forming a faint donut-shaped ring of charged particles similar in shape to Jupiter's own, though built from water rather than from volcanic sulfur and sodium. This discovery, made by the Cassini spacecraft, was one of the more unexpected findings of the entire mission, since nobody had predicted that a small, icy moon, barely 500 kilometers across, could be actively supplying material to shape the magnetic environment of the giant planet it orbits. Saturn's magnetosphere, as a result, carries a signature almost entirely different in chemistry from Jupiter's, even though both are generated by the same basic mechanism deep within a planet built from the same two elements. A small moon's quiet plumes turn out to leave a mark on a magnetic field vast enough to be measured from spacecraft still traveling between the planets. Saturn's rings, the feature that makes the planet instantly recognizable even to people who know almost nothing else about astronomy, are not a solid disk, however solid they may look through a small telescope. They are built from an enormous number of individual particles, almost entirely water ice, with only a small admixture of rocky material, ranging in size from grains no larger than dust up to chunks the size of a house, each one following its own independent orbit around the planet. Sunlight, reflecting off countless trillions of these separate icy pieces, is what gives the rings their brightness, more reflective overall than the pale gold clouds of the planet they surround, which is part of why the rings can sometimes appear to outshine Saturn itself in certain telescope images. Despite spanning a diameter that would comfortably stretch most of the distance between Earth and the Moon, the entire ring system contains, if all its material were gathered together, only a small fraction of the mass of a single modest-sized moon, an enormous area. The reason Saturn's rings remain a scattered swarm of particles instead of gradually gathering into a single moon comes back to the same boundary described earlier during Jupiter's encounter with a doomed comet, the Roche limit. Saturn's main rings sit almost entirely within this limit, the region close enough to the planet that its gravity pulls harder on the near side of any small clump of material than on the far side, stretching and eventually breaking apart anything that tries to hold together there. Any icy fragments that begin to stick to one another inside this boundary are pulled apart again before they can grow very large, keeping the rings as a collection of small, independent pieces, rather than letting them consolidate the way material further out was able to when Saturn's actual moons formed. It is the same physics that tore a comet to pieces at Jupiter, playing out here on a much larger and much more visible scale. continuously enforced rather than a single dramatic event, preventing Saturn's rings from ever becoming anything more solid than they already are. The rings are not a single unbroken sheet either, but are divided into distinct sections separated by gaps, the widest and most obvious of which is the Cassini division, a dark band roughly the width of the entire continental United States, discovered by the astronomer Giovanni Cassini in 1675, using nothing more than an early telescope. A narrower gap, called the Encke Gap, found further out in the rings, is kept clear by a small moon called Pan, orbiting directly within the gap and sweeping up or scattering any ring material that drifts too close to its own path. The way a snowplow keeps a lane on a road clear by continuously pushing material aside. Several other small moons, sometimes called shepherd moons, perform similar work at other gaps and edges throughout the ring system, their gravity confining and sculpting the icy particles into sharp boundaries that would otherwise blur and spread outward over time. Even something as apparently simple as a gap in the rings turns out, on closer inspection, to be actively maintained rather than simply empty by accident. For all their enormous width, Saturn's main rings are extraordinarily thin, in most places no more than about 10 meters from top to bottom, despite spanning a diameter of more than 270,000 kilometers. A ratio so extreme that if the rings were shrunk down to the width of a sheet of paper, that same scale would make the paper many kilometers wide. Each particle within the rings follows its own orbit according to the same laws that govern any object circling a planet, meaning particles closer to Saturn complete a circuit faster than particles farther out, a difference in speed that keeps the whole system from behaving like a single rigid disk, even though it appears solid from a distance. Collisions between neighboring particles, gentle and constant, help keep the rings confined to this remarkably thin, flat plane over time, smoothing out any particle whose orbit strays too far from the average. The result is one of the flattest structures known anywhere in the solar system, built entirely from countless individual pieces of ice that have never once been required to touch each other permanently to hold their shape. How old Saturn's rings actually are remains an open question, and one that data from the Cassini mission complicated rather than settled. For decades, the rings were generally assumed to be roughly as old as Saturn itself, formed alongside the planet more than 4.5 billion years ago. Cassini's final measurements of the ring's total mass, taken during its last close orbits before the mission ended, suggested they might contain too little material to have survived that long relatively unchanged, pointing some researchers toward a much younger age, perhaps only a few 100 million years, possibly the shattered remains of a moon or comet that wandered too close and crossed the Roche limit described earlier. Other researchers have pushed back against that younger estimate, arguing that certain processes could preserve an old ring system in a form that only looks young by some measures. Neither side has fully settled the argument, and the true age of the rings remains one of the more actively debated, open questions left behind by a mission that otherwise answered a great many others. Spectroscopic measurements of sunlight reflecting off Saturn's rings show that the material making them up is overwhelmingly water ice. In many places, more than 90% pure, with only a small admixture of rocky or carbon-rich dust darkening certain regions unevenly. That purity is part of why the rings appear so bright, compared with almost anything else in the solar system, since clean ice reflects sunlight far more efficiently than rock or metal does. Some regions of the rings appear noticeably dirtier than others, a patchiness that researchers attribute to slow contamination from micrometeoroid dust drifting in from outside the system over long stretches of time, gradually darkening the purest ice unevenly, depending on how exposed different parts of the rings are. Tracking exactly how quickly that contamination builds up has become one more piece of evidence used in the argument over the ring's true age. Since a ring system billions of years old should, in principle, have accumulated considerably more outside dust than one only a few 100 million years old. At Saturn's North Pole sits one of the strangest weather features found anywhere in the solar system. A persistent, six-sided pattern of jet stream wrapping around the pole in almost perfectly straight sides and sharp corners, rather than the smooth curve any ordinary storm would trace. First noticed in images taken by the Voyager spacecraft in the early 1980s, the hexagon was confirmed still present, largely unchanged in shape, when the Cassini spacecraft arrived decades later and was able to observe it continuously over years rather than during a single brief flyby. Unlike a storm on Earth, which forms, moves, and dissipates within days, this pattern has held its six-sided shape for as long as it has been observed, rotating in place at almost exactly the same rate as the planet's own interior, rather than drifting or gradually smoothing into a circle the way intuition might expect a fluid pattern to behave over such a long stretch of time. The hexagon is wide enough that nearly 4 planets the size of Earth could fit inside it, and observations suggest the pattern extends surprisingly deep into the atmosphere below the visible cloud tops, rather than being a thin surface feature confined only to the topmost layer of cloud. Laboratory experiments on Earth using rotating tanks of fluid to mimic the physics involved have managed to reproduce hexagonal and other polygonal patterns under the right conditions, showing that a jet stream moving at a particular speed relative to the rotation rate of the fluid beneath it can naturally settle into a shape with straight sides and corners instead of a smooth circle. Even with that laboratory support for the general mechanism, the exact reason Saturn's version has stayed so stable for as long as observations have existed, without slowly drifting into a different shape or losing its sharp corners, is still not completely understood. One more open question left behind at a pole that has now been watched carefully for the better part of half a century. Titan, the largest of Saturn's moons and the second largest moon in the entire solar system, stands out from almost everything else in this system for a very particular reason. It actually has a surface, wrapped in an atmosphere thicker than Earth's own, composed mostly of nitrogen, with a haze of organic compounds giving it a hazy orange color from outside. Titan's surface below that atmosphere includes lakes and rivers, though filled with liquid methane and ethane rather than water, since temperatures at Titan's distance from the Sun are far too cold for water to remain a liquid at the surface. Mountains, dunes built from hydrocarbon particles rather than sand, and river channels carved by flowing liquid have all been mapped by spacecraft, describing a landscape alien in its chemistry, but recognizably shaped by the same kind of processes, rain, rivers, and erosion that shape landscapes on Earth. Titan is not a gas giant. It is, in fact, the clearest counterexample nearby, a moon in the same system where a flaw was there to be found all along. In January 2005, the Huygens probe, carried across the solar system, attached to the Cassini spacecraft and released for its own final descent, did what the earlier Galileo probe at Jupiter never managed. It survived the fall through an atmosphere and actually touched down on solid ground. Huygens parachuted through Titan's thick nitrogen atmosphere for roughly 2.5 hours, photographing what appeared to be dry riverbeds and a landscape of small, rounded stones on the way down, before landing gently enough on a soft, damp surface to continue transmitting data and images for more than an hour afterward. It remains, to date, the only spacecraft ever to land successfully on a world in the outer solar system, and the images it sent back, showing an actual ground beneath an actual landing site, stand in direct contrast to everything found by descending into either of the two giant planets themselves. Titan has a flaw. Jupiter and Saturn do not, and never will, however far any future probe manages to travel into either of them. Enceladus, a small icy moon only about 500 kilometers across, turned out to be one of the most surprising discoveries of the entire Cassini mission, when the spacecraft's cameras spotted plumes of water vapor and ice particles erupting from cracks near its south pole, jetting out into space at speeds fast enough to escape the moon's weak gravity entirely. Those plumes are now understood to come from a liquid water ocean hidden beneath Enceladus's icy shell, kept from freezing by tidal flexing from Saturn's gravity, similar in principle to the tidal heating that keeps Io volcanic and Europa's ocean liquid at Jupiter. Cassini eventually flew directly through several of these plumes, sampling their composition with instruments not originally designed for the task, and detected simple organic molecules and evidence of chemical activity happening at the boundary between Enceladus's rocky core and its ocean above it. Material from Enceladus's geysers, spread thinly around Saturn, also supplies much of the fine, icy dust that makes up Saturn's broad, faint E-ring, connecting a small moon's quiet eruptions directly to the shape of the ring system visible from Earth. The Cassini spacecraft arrived at Saturn in 2004 after a 7-year journey and spent the following 13 years in orbit, becoming by far the most thorough study any spacecraft has made of the ringed planet, its rings, and its extensive family of moons. Over that time, it discovered new moons, mapped the rings in extraordinary detail, watched seasons change slowly across Saturn's northern and southern hemispheres, and delivered the Huygens probe safely to Titan's surface. By 2017, with its fuel supply running low, mission controllers faced the same decision engineers had made with Galileo at Jupiter 14 years earlier, and chose the same answer. Rather than risk an uncontrolled crash onto Enceladus or Titan, and any chance of contaminating either moon, they steered Cassini directly into Saturn's atmosphere. The spacecraft transmitted data for as long as its instruments could survive the increasing heat and pressure, sending back readings from closer to Saturn than any previous mission had ever gone, before finally burning apart and falling silent. The same ending that had already met its counterpart at Jupiter, deliberately sent into a fall with nothing at the bottom of it to arrive at. Pioneer 11, already mentioned earlier as it swung past Jupiter in 1974, went on to become the first spacecraft ever to reach Saturn, arriving in September 1979 after using Jupiter's own gravity years earlier to bend its path onward toward the second giant. Its instruments discovered a previously unknown thin outer ring, later named the F-ring, and confirmed that Saturn's magnetic field, like Jupiter's, was strong enough to trap significant radiation, information that helped engineers plan safer trajectories for the two Voyager spacecraft following not far behind it. Pioneer 11's cameras were basic, and many of its early images of Saturn's rings looked blurred and indistinct compared with what later missions would achieve. But as the very first close look any spacecraft had taken at this second giant planet, even a modest set of readings carried enormous scientific value simply for being first. Having already visited one bottomless giant, Pioneer 11 became the first machine in history to confirm that a second one, further out and ringed in ice, worked according to much the same rules. Voyager 1 reached Saturn in November 1980, using the encounter partly to conduct a close flyby of Titan specifically, a decision that bent its trajectory sharply away from the plane of the solar system and ended any chance of it visiting Uranus or Neptune afterward, a trade mission planners considered worthwhile given how much scientific interest Titan's thick atmosphere held at the time. Voyager 2 arrived 9 months later, following a very different path that kept it within the plane of the solar system and allowed it to continue onward afterward to Uranus and eventually Neptune, becoming decades later still the only spacecraft ever to visit either of those two farther worlds. Together, the two Voyagers photographed Saturn's rings and moons in far greater detail than Pioneer 11 had managed, discovered several new small moons, and returned the first clear images of the hexagon-shaped pattern already circling Saturn's North Pole, even then, decades before Cassini would spend years studying it up close. Roughly once every 20 to 30 years, Saturn produces an enormous storm system nicknamed a Great White Spot, a burst of far more dramatic weather than the planet's usually calm, pale clouds suggest is possible, erupting suddenly and spreading rapidly until it can be seen wrapping partway or even fully around the planet. These outbursts appear tied to Saturn's long seasonal cycle, thought to build up gradually as warm, moist air rises from deeper in the atmosphere and finally breaks through the stable layers above it in a single dramatic event rather than the more continuous turbulence Jupiter's clouds display. Several such storms were recorded by observers on Earth across the 20th century, spaced out unevenly but roughly in line with the pattern, and each one has been better studied than the last as telescopes and later spacecraft cameras improved. The most recent, and by far the most closely studied of these outbursts, began in December 2010 and was watched continuously by the Cassini spacecraft, already in orbit around Saturn at the time, for the better part of a year as it grew. Within weeks, the storm's head had expanded to cover an area larger than Earth, and its tail eventually stretched all the way around the planet, wrapping back around to meet itself and forming a single continuous band of turbulence circling Saturn's northern hemisphere. Cassini's instruments tracked lightning within the storm, thunder detected indirectly through radio bursts far stronger than anything measured on Earth, and temperature spikes high in the atmosphere above the storm's core, caused by the sheer amount of energy being released below. By a wide margin, that was the best documented storm Saturn has ever produced, observed from beginning to gradual fading nearly a year later by a spacecraft that happened to already be exactly where it needed to be to watch the whole event unfold. Among Saturn's more than 270 confirmed moons, Iapetus stands out for an appearance unlike almost anything else in the solar system. One hemisphere is dark as coal, reflecting only a small fraction of the sunlight that strikes it, while the other is bright, icy white, reflecting most of the light that reaches it. A contrast sharp enough that early observers using primitive telescopes noticed Iapetus brightening and dimming dramatically depending on which side happened to be facing Earth as the Moon orbited. The likely explanation, confirmed in more detail by Cassini's close flybys, involves dark dust drifting in from a much smaller but far more distant moon called Phoebe, settling preferentially onto Iapetus's leading hemisphere as it orbits. The darkened ice then absorbs more sunlight, warms slightly, and evaporates away even faster than the surrounding bright ice, deepening the contrast further over time. A moon shaped, in effect, by dust falling from somewhere else entirely, slowly painting one half of it a different color from the other, across a very long span of time. Occasionally, dark, wedge-shaped markings called spokes appear briefly across sections of Saturn's rings, radiating outward like the spokes of a wheel, rather than following the usual circular flow every other feature in the rings obeys. First noticed by the Voyager spacecraft in the 1980s, and studied again in far greater detail by Cassini decades later. Spokes are thought to form when fine, electrically charged dust is lifted briefly above the plane of the rings, likely triggered by tiny impacts or changes in the local electric environment tied to Saturn's own magnetic field. They appear and fade within a matter of hours, far too quickly to be explained by the normal orbital motion of ring particles, and their frequency changes noticeably with Saturn's seasons, appearing far more often around the planet's equinox than at other points in its long orbit. Even a ring system built almost entirely from the simple, predictable physics of countless orbiting ice particles turns out to have room left over for a genuinely strange and still not completely explained phenomenon happening briefly across its surface. Mimas, one of Saturn's smaller inner moons, is dominated by a single enormous impact crater named Herschel, stretching across roughly a third of the moon's entire diameter, with walls several kilometers high and a central peak nearly as tall as Mount Everest rising from its floor. The crater is large enough, relative to Mimas's small size, that the impact which created it came close to shattering the moon entirely, leaving fractures on the opposite side of Mimas that some researchers believe were caused by shock waves traveling all the way through the small body from the original collision. Mimas orbits well beyond the outer edge of the rings, yet its gravity still keeps one of their widest gaps clear, nudging any ring material that falls into resonance with its orbit onto a different path, unlike the smaller moon Pan, which clears the Encke gap from inside it. A modestly sized moon, then, carrying one enormous scar from its past, and quietly shaping the boundary of the rings it orbits alongside, all at the same time. In 2008, data from the Cassini spacecraft suggested that Rhea, Saturn's second-largest moon, might carry a faint ring system of its own, an unexpected find that would have made it the first moon known to have rings encircling it. The evidence came from a dip in the flow of electrons detected near Rhea, consistent with charged dust particles orbiting the moon in a thin disk and absorbing some of that electron flow as Cassini passed through the region. Later, more careful observations, including images taken specifically to search for any ring material directly, found nothing. And the electron dip was eventually explained by other processes instead, closing the case on what would have been a striking discovery. The dead end shows how easily even a well-instrumented spacecraft, orbiting for over a decade, can be misled by an intriguing signal that later evidence fails to confirm, and how some of the more dramatic possible discoveries raised during a long mission simply do not survive a second, closer look. Everything followed through Saturn across this second half of tonight's journey traces the same basic shape already found at Jupiter. An atmosphere with no bottom, a magnetic field generated by metal made from hydrogen, and a family of moons and rings shaped by the same gravity that refuses, at the planet's own center, to settle into anything solid. What makes Saturn distinctly itself, rather than a smaller repeat of its neighbor, is everything visible from outside. Rings bright and wide enough to be the first thing anyone notices, a six-sided pattern of cloud unlike anything else known anywhere in the solar system, a magnetic field aligned in a way current theory still cannot fully explain, and a large moon, Titan, manages to have the one thing neither giant planet itself will ever offer a probe descending into it, an actual surface to land on. The two planets share nearly the same raw material and the same handful of physical rules, yet still look recognizably different from one another in almost every way that can be seen from outside. Step back from both planets now, and a shared origin becomes clear. Jupiter and Saturn are both built overwhelmingly from hydrogen and helium, nearly the same mixture found in the Sun itself, gathered from the same cloud of gas and dust that formed the entire solar system more than 4.5 billion years ago. Neither planet ever grew massive enough to ignite the fusion that powers a star, leaving both of them as enormous leftover samples of the material the solar system was originally built from, essentially unchanged in bulk composition since they first came together, unlike the rocky planets closer to the Sun, which lost most of their original hydrogen and helium to space long ago. Looking closely at either Jupiter or Saturn is closer to looking at a sample of the very earliest solar system than looking at almost anything else still nearby, preserved not on a shelf, but inside two enormous, slowly cooling worlds that have simply been sitting in the dark, gradually giving off the heat of their own formation for billions of years since. Both worlds are still actively separating hydrogen from helium deep inside themselves even now, droplets of helium condensing out of the surrounding fluid and sinking slowly toward the center, releasing energy as they fall and keeping each planet measurably warmer than sunlight alone could ever make it. Saturn, as already described, appears to run this process more efficiently than Jupiter does, likely because its lower internal pressure allows the separation to begin at a shallower, cooler depth, where hydrogen and helium are more reluctant to stay mixed together. The result is visible from the outside in both cases, in the form of extra infrared heat radiating from each planet. But the underlying cause, a slow and completely silent rain occurring nowhere anyone could ever watch it directly, is identical in kind, if not in exact strength. Two planets fall gently apart from within, each one warmed by an ongoing separation of its own two main ingredients, at a pace set by nothing more dramatic than gravity and pressure working steadily on the very lightest elements there are. Both planets generate their magnetic fields the same basic way, through motion inside an ocean of metallic hydrogen, and together their magnetospheres dominate an enormous stretch of the outer solar system, overlapping in influence, even though the two planets themselves sit hundreds of millions of kilometers apart. Jupiter's field is by far the stronger and larger of the two, its magnetic tail stretching out past Saturn's own orbit entirely, meaning that Saturn, at certain points along its own path around the Sun, actually passes through the very edge of Jupiter's magnetic influence before continuing on through its own. Spacecraft traveling between the two planets, or passing through the outer solar system on their way further out, have to account for both fields when planning a safe trajectory, since either one is capable of damaging sensitive instruments if a mission strays too close without adequate shielding. Between them, these two magnetic fields, generated by nothing more exotic than pressurized hydrogen, shape the environment of the outer solar system across a volume that dwarfs the orbits of every rocky planet closer to the Sun combined. 5 spacecraft in particular carried our questions out to these two worlds across more than half a century of exploration. Pioneer, first and simplest, proved that a spacecraft could survive the journey and the radiation at all. Voyager, following soon after, returned the first genuinely detailed pictures of both planets and their moons within the space of only a few years. Galileo and Cassini each settled into orbit for years at a time, mapping their respective planets and moon systems in extraordinary detail, before both, in the end, were deliberately steered into the very atmospheres they had spent years studying, becoming part of the same endless fall they had been sent to observe from a careful distance. Juno, the most recent of the 5, spent the better part of a decade finding new detail in a magnetic field and a core that refused to behave the way earlier, simpler models predicted. Between the 5 of them, no square kilometer of either planet's cloud tops remains entirely unphotographed. And yet, neither planet's actual center has ever been reached, or ever will be, by anything built to survive the attempt. Every spacecraft ever sent to land on Mars, or planned to eventually land on a rocky moon, has been built around the assumption that somewhere along its descent, a surface will eventually arrive to catch it, whether gently with parachutes and retro rockets, or, in earlier decades, by crashing into it directly. No mission has ever been built with that same assumption for Jupiter or Saturn, because no engineer designing a probe for either planet has ever had reason to expect a surface to design a landing for. A probe aimed at either giant can only ever be built to fall, gathering data for as long as its instruments survive the increasing heat and pressure, and then to fall silent, exactly as Galileo's small atmospheric probe did in less than an hour at Jupiter in 1995. It is one of the clearest practical differences between exploring a rocky world and exploring a gas giant. One kind of mission ends with a landing, and the other kind of mission simply ends. The same boundary that tore a comet apart at Jupiter and keeps Saturn's rings from ever gathering into a single moon applies, in principle, to both planets equally, a simple consequence of how strongly each one's gravity pulls on anything passing close by. Jupiter's version of this boundary produced a chain of shattered comet fragments and a set of scars that faded from its clouds within months. Saturn's version produced something far more enduring and far more visible, an entire system of rings, spread thin and bright enough to be the first thing most people picture when they hear the planet's name. The same underlying physics, applied to slightly different circumstances and slightly different starting material, produced two very different outcomes. One, a brief and violent event, the other, a slow, quiet, and apparently very long-lived structure, still being argued over by scientists today. Even something as simple as a boundary, defined purely by gravity, can shape two neighboring planets in strikingly different ways, depending on what happens to be nearby when it matters. Neither of these two worlds has finished offering up its questions. Saturn's ring age remains undecided, caught between a mass measurement that suggests youth and an intuition, still defended by some researchers, that 4.5 billion years of history is difficult to erase that completely. Jupiter's core remains diluted and poorly defined rather than sharply bounded, a finding still being incorporated into new models of how giant planets form in the first place, not just around our own sun, but around other stars as well. Saturn's magnetic field remains almost too perfectly aligned with its own spin for current theory to comfortably explain, and Jupiter's fastest winds and deepest storms were tracked year after year by a spacecraft that kept finding new detail on every close pass. None of tonight's facts close off further study. Each one describes only how much has been learned so far about two worlds that, despite more than half a century of visits, remain very far from being fully understood all the way down. Further exploration is already underway. The JUICE and Europa Clipper missions, both mentioned earlier, are currently crossing the solar system toward Jupiter's icy moons rather than the planet itself, continuing a shift in focus from the giant planets to the smaller worlds orbiting them, places considered more promising in the search for conditions that might once have supported something more than plain chemistry. A separate mission called Dragonfly, a drone-like rotorcraft rather than a wheeled rover, is being built to fly directly through Titan's thick atmosphere once it arrives, hopping from site to site across that moon's actual surface in a way no previous mission has attempted anywhere in the outer solar system. No mission currently funded is aimed at descending any further into either Jupiter or Saturn than Galileo and Cassini already managed. and any future attempt would face precisely the same limitation both of those missions eventually met: a flaw that never arrives, however much better the engineering protecting the instruments becomes. Titan, so close to Saturn that it orbits well within the giant planet's own magnetic influence, has lakes, rivers, mountains, and a surface solid enough for a spacecraft to land on gently and keep transmitting for more than an hour afterward. Jupiter and Saturn themselves, the two enormous worlds Titan and every other moon in this system orbit around, offer nothing of the kind. The absence of a flaw is not a universal rule of large objects in space. It belongs specifically to these two planets. Worlds built almost entirely from gas and metal rather than rock and ice. And to any other gas giant like them that might be found circling some other star, still waiting for a name and a spacecraft of its own. Two vast worlds, then, built from nearly the same material, warmed by nearly the same slow rain of helium, wrapped in magnetic fields generated by the same metal made from the lightest element there is, and both offering, at the end of every possible descent, nothing more solid to arrive at than a little more pressure and a little more heat than the layer just above it. Jupiter answers the question of how far down with a diluted core that resists being measured precisely. Saturn answers the very same question with a fuzzy, still uncertain center of its own, wrapped in rings and a six-sided pattern of cloud that nothing else nearby has ever quite matched. Between the two of them, every spacecraft ever sent has managed only to describe the fall a little more precisely, never to reach anything waiting at the bottom of it, because nothing of the kind has ever been there to reach. The floor these two planets never had is, in the end, the entire story. We began tonight at the very top of Jupiter's clouds and went straight down through gas that slowly stopped behaving like gas, through an ocean of hydrogen pressed until it carried electricity like a metal, past a probe that fell for less than an hour before it could send back nothing further, and toward a core too spread out to ever be pinned to a single point. We came back out to 4 small worlds, discovered by one man with an early telescope, to a faint ring of dust, and to a comet torn apart by nothing more than gravity and distance before it fell in pieces across 6 days in 1994. Then we crossed to Saturn and made the same descent again, through a paler, quieter atmosphere, hiding the same bottomless structure underneath. Past a magnetic field too well aligned with its own spin for anyone to fully explain. Out to rings built from countless separate pieces of ice, and up to a 6-sided pattern of cloud that has been turning at the pole for longer than any of us have been alive to watch it. 2 spacecraft, sent to study each of these worlds for years, ended their missions the same way, deliberately falling into the very atmosphere they had spent so long describing, disappearing into the same endless drop that this entire journey has followed twice tonight. If this is the kind of quiet you would like more of, the subscribe button will be waiting whenever you decide to use it. Rest well and sleep gently into whatever is still turning slowly overhead.